Anyone else got that?
Yeah.
Okay, so this is gonna be, this is pascals, so 2 times, that's gonna be 2.026, 2.026, and then this is 10 to the 5th, right? And then the volume is gonna be 0.306, and then this is in units of meters cubed. So almost try visualizing as if you're doing an Excel graph of this, you know. I think that's it. As far as state variables, now we know the original volume, original pressure, original temperature. The temperature you can put right at that corner, 298.15, right? So it doesn't go on the graph, but it is an important state variable of the gas, right? So now if you're going isobarically, 3 times the volume, so we already know the volume is gonna be 3 times this, right? So then that's gonna be 0.918, right? The pressure is gonna stay the same, so what's gonna be the temperature, right? So PV is nRT, so if the pressure stays the same and the no moles stay the same, volume is proportional to temperature. So if the volume triples, the temperature triples. See? So the temperature triples, but that doesn't mean the temperature becomes 75 Celsius, right? The temperature in Kelvin triples. So that really becomes hot, right? So 298.15 times 3, 894.45 Kelvin. See why it's good to put the temperature there, right there on the corner. And then now what happens? Then you go down isovolumically to the same temperature. It said to the same temperature that you began. Okay, well then what should the pressure be over there? Well, since this is isothermal, right, what should happen? This graph should obey the equation, right? P1V1 is P, this one we can call P3V3, right? P3V3, and since this is 3 times that, that means P3 needs to be 1/3 of P1, right? So this one, pressure needs to be 3 less than this, so that the volume here is 3 more than that, and the temperature is the same, you see. So, so it's about, yeah, 1, something like this visually. 1, 2, 3. So, so then what's the pressure here gonna be? So it's 2.026 divided by 3. 0.675. Of course, these are all 10 to the 5th, right? So it's just 1/3 of this pressure. Everyone getting what I'm doing? So if your graph is complete and accurate, it's usually going to help with a lot of your calculations. So why don't you take a look what I've done so far, see if you're understanding it. So far, so good? Yeah? Okay, so now how do I find the work done by the gas in that stage, in this stage, in this stage? W1, W2, W3. Okay, what's the work done by the gas in the first stage? The first stage is simple isobaric, so it's P1 times the change in volume, right? Because it's a straight line. P1, change in volume. So P1 is going to be 2.026 times 10 to the fifth. The volume is going to be the change in volume 0.918 minus 0.306 meter cubed. Okay, so those my hundred and 123.99 kilojoules, right? Since the numbers are big, I prefer to have a kilo there. That's kilojoules of energy. Now, if I wanted to, I could convert that to calories of heat, calories of work. I can say 4.186 kilojoules is one food calorie. If I was interested in a food calorie, right? So then I would divide that by 29.6 food calories. All right. So our biological systems in our body do this kind of work too. You know, the Krebs cycle and all of that. So all this work that we're doing, we're using up the calories that we're eating. So we're kind of an engine too. You know, but of course our Krebs cycle and the other cycles, they're much more complex than this. So we're a thermodynamic engine, biological thermodynamic engine. Okay, so now that's W1. The work done in the second stage is isovolumically down, so it's 0, right? Work done in the third stage is what? It's going back, so the gas is doing negative work. You're the one doing the work, but the gas is doing negative work, right? So what's the equation for that? Negative nRT3 ln of V2 over V1. Or I could just put it this way, nRT3 V1 over V3. In other words, nR, the temperature that it had when it began the isothermal process, because that's constant, times the ln of the final volume over the initial volume at the V3, right? So when you do that, it's already going to come up negative because the V1 is less than V3. And when this is a fraction, ln of a fraction is negative, right? So then it's going to be W3, the number of moles of the gas, 8.314. The temperature of the gas when it began its isothermal state was the initial temperature, right? 298.15. ln of what? The volume V1 is 1/3 of the volume V3, right? So ln of 1/3. So of course that's going to be negative ln of 3. Negative 68.08 kilojoules. That's the work done by the gas. And the work done on the gas, by the gassier, what was the What was the answer to the first one? Did I not write it? Oh, here it is. 123, the work done by the gas. So overall, the total work done by the gas is what? Positive, right? Because it's the area under the graph. So this is literally the total work done by the gas, right? Work total by gas is going to be what? This minus this. Okay, now I do the heat into the gas in each stage. What's the heat into the gas? Q1. Okay, so during the isobaric process, what's the heat into the gas? What form of the first law of thermodynamics should I use? Well, you know what? It really doesn't matter what form. I can just use whichever form I like. Which form is the best to remember? Well, whichever one you like to remember that one, right? So Q into gas is equal to the change in internal energy of gas plus work by gas. That's one form. I like remembering that one because I think of a flame and then I say, okay, if you have a flame under a chamber, some of that heat goes into the gas and then it allows the gas to do work. You see, so that form I like, you know. So now I can say Q1 is equal to the change in internal energy of the gas, work by the gas. So work by the gas I already know is 123 during stage 1, right? So 123.99 kilojoules. So what's the change in internal energy of the gas? How do we find that? Change of internal energy of gas is going to be well, now it does depend if it's monatomic or diatomic, because it has to do with if the internal energy is made up of kinetic energy plus potential energy. Kinetic energy plus potential energy. So if it's monatomic, it doesn't have potential energy, right? So potential energy is 0 for monatomic. Then the kinetic energy is going to be equal to 3 halves for each degree of freedom, right? You have half RT. Half nRT, so then you have 3 halves RT for 3 degrees of freedom. If you're moving this way, your kinetic energy yields half RT. If you can move in 2 dimensions, it's 2 halves RT, and then 3 dimensions is 3 halves nRT. So 3 halves nR delta T. Now if you introduce potential energy, then that's going to be 5 halves nRT for diatomic gas. Okay, so that's kind of bringing in chapter. We almost have to bringing in what we're going to discuss in chapter 21 in chapter 20. So then they say, okay, change in internal energy. So for now, we're just going to do monatomic gases. For monatomic gas is 3 halves nR delta T. Okay, so then we're going to do. So 3 halves number of moles times 8.314 times the change in temperature of the gas, which is 894.45 minus 298.15. 894.45 minus 298.15, change in temperature of the gas. So that's the change in internal energy of the gas. So because it was isobaric, all the heat you put in didn't go into changing the temperature. Part of it went into the gas doing work, you see? And part of it went into the gas heating up. That's what's exactly happening there. So Q1 into gas is going to be what? So once I calculate this, then I'll add it to the kilojoules. So that's 185.91 kilojoule. (185.91 kilojoule). So that means that the heat I put in is the sum of the work done plus how much energy it increased. So what I do usually is I go back to the PV diagram and I just do like a little wiggle sign and I say this is the heat that I'm putting into the gas. Q into gas. In other words, that's the driving force for the engine. So in the case of a car engine, if I was going to use this cycle as a car engine cycle, I would have to burn some gasoline or something that would give me enough heat to pour into the gas to start the cycle, you see. So you can't have an engine unless you have something to start the engine. In this case, that's the heat. So this is the real thing that starts, the kick starts the engine, you see. And you do that by burning some form of fuel. Or in the case of electric car, electric fuel, all right, solar fuel.
Yeah, like you heat it up to 3 times the volume, right? So why is that a 3/2? And
Oh, that one is wait till chapter 21 where I go into monatomic gases into the theory. What we're going to see is each degree of freedom of a gas gives you half nRT.
Oh, half that. So we haven't.
And then if you have three-dimensional monatomic gas, of course, three-dimensional.
So can I compare it to? It's pretty much a 1/2 nRT. Like,
It's kind of related to that, yeah, probably, a little bit.
Because I don't know where is that.
The half coming from, yeah.
Anyway.
They might cover that in Chem 101 or 102, I don't know where they cover it, but we're gonna cover it definitely in chapter 21. Okay, so then you get to the heat in the second stage, Q2, is going to be, so this is isovolumic, right? So then it's going to be, work is 0, so it's just going to be delta E. Right? Delta E of gas, no work done by the gas. And delta E of gas is just going to be 3/2 NR again. 3/2 NR times delta T, but then you're going back to its original temperature. So 298.15 minus 894.45. So it's actually just this part, but it's negative, right? So that means Q2 is going to be negative 185.91 kilojoules. So now the gas is expelling that out. You see? So the arrow is the opposite direction. Because it's a hot gas, the gas is expelling that out, so that's going to be, you know what, let's write down here the numbers. 309.9 kilojoules is coming in, And now 185 is going out. That's the equivalent of what comes out of your muffler, the heat that you expel out to the surrounding, right? All cars and engines have to do that. They take heat from the surrounding, and they always expel out to the surrounding. And in the car, it's the muffler. You expend out the heat over there. You dump it back out. Okay? So then that's it. So we already know the Q2. Okay? And then Q3 is going to be now it's isothermal Q3. So isothermal, that means the temperature is not changing, right? So delta E is 0 now. So the Q3 is just going to be work by gas in the third stage. Work 3. Right? Because delta E is 0. So then what was W3? Negative 68. So then that's, you dump out that much too. So negative 68, so 68 comes out. 68.08. See, but this, the sum of these two is not equal to that, right? So you have to put in 309 joules for the engine to get going, then you're expelling out 185.68, that's about 240 or 250, something like that, right? So there's a net heat that the gas has gained, and the gas has done some work based on that, right? So now what are the delta E of the gas? Well, we already know that pretty much, because as you're doing this, you have to do that, right? They go together. So, oh, you know what? Let's calculate Q total. Q total into gas is going to be the Q1 plus Q2 plus Q3. Okay. Boom. So that's the total net heat that the gas has gained, right? Now delta E, 1. Well, that one we should already know. That one was this one, right? The 185.91. What's delta E2? And that one was this one, right? It was basically the opposite of the first one. So negative 185.91 kilojoule. Delta E3, 0, because it was isothermal, right? Delta E total is what? Well, delta E total, if you return back to the same state that you began, we're assuming that you can't come back to the same state with the same pressure, same volume, same temperature, right? So it is called a reversible cycle. So if it is completely the same state, delta E total should always be 0, because you come back to the same temperature, right? So this is 0. So this confirms that we're doing something right, at least, right? Because this cancels this and this is 0. So this should always be 0. So that's good. So the last thing to do is the efficiency of this engine. If we treat this as an engine, how is efficiency defined? 100% times the work by the engine divided by heat into the engine. In other words, how much work did this engine do in one cycle, right? and then divided by how much heat I had to put into it to drive the cycle. So efficiency, work by the engine, so what's that going to be? That's going to be the W total. Where was that? Do we calculate W total? W1, W2, W3, and W total 55, right? So that's how much the total work done. That's W1 plus W2 plus W3, that's the total work done, which is the area under the graph. Area under graph is the total work, right? So then what would happen? Area under graph. So then that's going to be the 55.91. And then the heat into the engine is what initially drives the motion, right? Then that's 309.9.
No. Wouldn't it be total? Oh, it's
No,
into.
because the other ones are the ones that dumped out.
Okay.
So it took 309. %, that's about the regular efficiency of a car, right? 18%. So we put a sad face because those are heat engines, right? It's not that efficient. Okay. Cool stuff, huh? Good total cycle. Now, can we change those three things that we're doing, change the order of them, and change possibly the efficiency of that engine? Yeah. We could change, like maybe go up isovolumically, go across isobarically, come down isothermally. In other words, just the three same cycles, but do them in different orders. And maybe we get a better engine out of that, you know? Or maybe go this way, go this way, go this way. Yeah, that would be one way. We could go, can't change it too much more. Go this way. How about if we go this way, and back? But we don't want the network of the engine to be negative. So we want the area under the graph to be positive, right? So if we're trying to make an engine out of it, we could go up this, and then this is the area under the graph. So this is positive. If we go like this, this is the area of the graph. So the engine does positive work. But if we do it this way, no, that'd still be negative, right? No, that'll be negative work done by the gas. That's the area under the graph. Then going back is doing negative work. So now this is going to be negative work. Negative work by engine. Work total engine is negative. Here the work is positive. Right? Because going up, you're doing this much work under the area under the graph. Going back, you're doing a bigger work, negative. It cancels it out and it becomes negative. So this one will be good if you want to use the engine as a refrigerator. Running it backwards, it becomes a refrigerator. You do work, but the refrigerator does negative work and it extracts heat from the system. You see? So these two are more a heat engine and this is a refrigerator. You see? So it depends on which order you do it. If the total area is positive, then it's a heat engine. Let me see. You could go down. You could go down and back up and across.